Hello my friends and welcome back to the You Can Do TV channel. Alpsson Aluminum, founded in 1985, operates as a high-capacity manufacturer of precision aluminum profiles in Turkey. The facility comprises 3 extrusion lines with an annual production capacity of 12,000 tons, complemented by 6,000 tons in anodizing and 10,000 tons in painting. Profiles with wall thicknesses down to 0.7 millimeters and weights of 40 grams per meter are produced, supporting a wide range of industrial applications. Surface finishing processes include anodizing, painting, foil coating, and metal finishing. Anodized profiles are processed under certified quality control procedures to ensure adherence to European standards. Surface colors include natural, yellow, brown, and black, with options for matte, glossy, brushed, or stainless steel effects. The anodizing and painting lines employ Machining is executed with 5-axis CNC equipment capable of simultaneous multi-surface processing, supporting both standard and custom part geometries. High-volume production is facilitated through part-specific tooling, reducing cycle times and operational costs. Inline assembly and specialized packaging systems are integrated to prepare products for deployment efficiently. The integrated production workflow, including extrusion, machining, anodizing, and painting, ensures dimensional precision, surface quality, and structural integrity. Profiles manufactured through this process meet high-performance requirements for mechanical strength, corrosion resistance, and aesthetic consistency, suitable for a wide range of industrial and architectural applications. Vertical painting lines utilize fully automated spray systems with multiple precision paint guns, enabling coating of profiles up to 7.5 meters in length at rates of approximately 1.2 kilograms per hour. Coating systems ensure uniform application, defect-free finishes, and enhanced surface durability. The aluminum rolling production process is a precise sequence of metallurgical and mechanical operations designed to transform raw material into high-quality aluminum coils and sheets. It begins with raw materials that undergo melting in large capacity furnaces, where strict temperature control ensures alloy uniformity. The molten aluminum is then transferred to holding furnaces to maintain stability before casting into slabs. These slabs serve as the foundation for subsequent rolling stages. Once solidified, the slabs are subjected to surface milling, a process that removes oxidation layers and impurities to achieve a clean surface. Homogenization heat treatment follows, equalizing the internal structure and improving workability. The slabs then undergo hot rolling, where they are passed through heavy mills at elevated temperatures to reduce thickness and refine grain structure. After hot rolling, the process advances to cold rolling. Here, aluminum coils are reduced further under controlled pressure to achieve precise thickness and enhanced surface quality. Degreasing treatments remove residual oils, while annealing restores ductility lost during deformation. Finishing operations ensure dimensional accuracy and product readiness. Slitting adjusts coil width to customer specifications, while tension leveling corrects shape irregularities. The final step is packaging, where coils are securely wrapped for protection during storage and transport. Each stage is carefully monitored to guarantee mechanical strength, surface integrity, and uniformity. Vaughan Electric's state-of-the-art motor repair facility is designed to overhaul large electric motors, including those exceeding 500 horsepower, restoring them to their original performance specifications. Their meticulous process ensures reliability and efficiency through a series of carefully executed steps, seamlessly blending precision and expertise. Each phase, from disassembly to final testing, is performed with advanced equipment and skilled technicians, guaranteeing a motor that operates at peak performance. The first step involves the careful disassembly and inspection of the motor. Technicians methodically take apart the motor to evaluate critical components such as the stator, rotor, bearings, and windings. By conducting detailed measurements, they identify any signs of wear, damage, or degradation. This thorough assessment forms the foundation of a tailored repair plan, ensuring that all issues are addressed to restore the motor's functionality. The precision of this initial step sets the stage for the subsequent phases of the overhaul. Once disassembled, all components undergo rigorous cleaning and stripping to remove contaminants like grease, dirt, and old insulation materials. Using advanced techniques such as ultrasonic and chemical cleaning, Vaughan Electric ensures that every part is free from debris. This step is critical not only for accurate inspection but also for preparing surfaces for recoating or re-insulation. A clean foundation allows for precise repairs and enhances the durability of the restored components, paving the way for the next stages of the rebuild. With cleaned parts ready, the rotor is placed on a CNC lathe for precise machining. Technicians remachine critical features like the shaft surface and fan slot, checking for concentricity and wear to ensure optimal performance. Dynamic balancing follows, ensuring the rotor operates smoothly at high speeds without vibrations. This meticulous attention to the rotor's condition is essential for maintaining the motor's stability and efficiency, seamlessly transitioning to further repairs. The rotor repair phase addresses any detected damage or wear. If needed, the rotor is rebarred and restacked to restore its magnetic properties, while the shaft is examined for straightness and corrected for any imperfections. These repairs ensure smooth operation and prevent future failures. Following this, high-quality bearings are installed to reduce friction and wear, and the shaft is checked for alignment and balance. This step minimizes energy loss and mechanical stress, ensuring the motor runs efficiently under demanding conditions. To enhance durability and aesthetics, components like the motor frame, end cover, and fan are repainted with specialized heat-resistant paint. This protects against corrosion and ensures the motor can withstand harsh environments. Concurrently, the stator, rotor, and other parts are cleaned again, and new bearings are lubricated with high-quality grease to extend their service life. These steps collectively contribute to the motor's longevity and reliability, setting the stage for final assembly. After repairs, the motor is reassembled with precision. Components such as the stator, rotor, bearings, end cover, and housing are carefully aligned and secured, with technicians verifying the fit and accuracy of each part. Dynamic balancing is performed post-assembly to eliminate vibrations, ensuring smooth operation and preventing premature bearing failure. This meticulous assembly process ensures the motor functions as a cohesive unit, ready for rigorous testing. The final phase involves comprehensive testing and commissioning. The rebuilt motor is run under load conditions to verify its performance against original specifications for voltage, current, and power output. Any discrepancies are addressed to ensure flawless operation before the motor is returned to service. Vaughan Electric's commitment to quality, supported by advanced testing equipment and experienced technicians, ensures that each motor is restored to peak performance. Through this seamless step-by-step process, Vaughan Electric transforms high-horsepower motors into reliable, efficient machines. Their expertise and attention to detail make them a trusted provider for large motor overhauls, delivering results that meet the highest industry standards and ensure long-term operational success. The erection of the 540 meganewtons pull-down forging press at Weber Metals in Los Angeles, a subsidiary of Otto Fuchs KG, represents one of the most ambitious industrial engineering projects in modern aerospace manufacturing. Described as the world's largest and most powerful hydraulic closed-die forging press, this machine delivers a staggering 540 meganewtons, 60,000 short tons, of press force, designed to meet the demand for increasingly large, complex, and high-performance aerospace components. The project, developed by SMS Group, was not only about building the largest press, but about ensuring maximum precision. Aerospace parts produced on this machine require the highest material grades and flawless geometries. For this reason, the design was approached backwards, starting from the customer's production needs and building the press around them. Construction of the press required 34 massive castings and forgings, each weighing between 100 and 310 tons, sourced from foundries in Korea and Great Britain. Despite their enormous dimensions, components such as conical guides had to be machined with tolerances accurate to hundredths of a millimeter. 4 tie rods, each over 25 meters long and 1 meter in diameter, provide the press with its exceptional stability. Logistics were equally complex. Components were transported across multiple continents for machining and finishing before arriving at Weber Metals for assembly. The press pit itself, excavated to a depth of 24 meters, houses the hydraulic systems and structural foundation. One of the most critical milestones was the lowering of the 200-ton lower crosshead into position using a mobile lifting tower, a process requiring meticulous planning and flawless coordination. This global masterpiece demonstrates SMS Group's unmatched expertise in heavy press technology. Through teamwork, precision, and proactive engineering, the erection continues on schedule, setting a new benchmark in aerospace forging capabilities. Brug cables employ CNC-controlled processes to produce high-performance cable systems for power transmission, industrial, and specialized applications. Their facilities in Switzerland, Poland, and China support the fabrication of cables spanning low voltage to extra-high voltage, up to 550 kilovolts. Production features automated extrusion, insulation, including cross-linked plastics, stranding, and shielding systems, followed by continuous quality assurance using geometry, insulation resistance, partial discharge, and voltage testing. Custom, engineered to order, capabilities enable development of tailored solutions, such as hybrid, weather-resistant, or EMS-compatible cables for diverse environments. Supported by rigorous ISO 9001 and 14001 systems, Brug Cables maintains high precision in assembly, material handling, and inspection to meet demanding international standards. The production of a 6000 LT enamel boiler requires advanced forming and welding technology to achieve both strength and durability. The process begins with steel plate preparation, where heavy-duty hydraulic presses are employed to shape conical heads and dished ends. Using a press-forming machine, the top and bottom domes are precisely formed, while a dished head rolling machine produces spherical segments that will serve as the boiler's caps. The cylindrical body of the boiler is created using a plate rolling machine, which bends thick steel sheets into a perfect cylindrical shell. Precision is essential to ensure roundness and proper alignment. At the same time, a tube bending machine is utilized to manufacture the helical coil heat exchanger that will be installed inside the boiler. These coils are formed from high-grade steel tubes, bent into spiral shapes to maximize heat transfer efficiency. Once the body, heads, and coil are fabricated, the welding and assembly stage begins. Automated submerged arc welding machines are applied to join the shell and dished ends, while the helical coil is mounted and secured inside. Non-destructive testing methods such as ultrasonic inspection are performed to guarantee weld quality. This structured process ensures that every Kubus boiler's end boiler, whether large-capacity 6000 LT units or smaller domestic models, meets stringent quality standards, delivering high durability, excellent thermal performance, and long operational life. After assembly, the boiler undergoes enameling and firing. The internal surfaces are coated with enamel slurry, then placed into a kiln for high-temperature firing at around 850 degrees Celsius. This vitrification process fuses the enamel with the steel surface, producing a glass-like protective layer that ensures long-term resistance against corrosion, scaling, and chemical attack. For smaller enamel boilers, the process is simplified. Hydraulic presses form the cylindrical body directly in two halves, which are then welded together along the seam. Support legs are welded to the base, followed by enameling, firing, and exterior painting. The next stage is finishing and painting. The exterior is coated with industrial-grade paints to provide corrosion resistance and enhance appearance. For large boilers, thermal insulation is applied, often by wrapping with protective fabric-based cladding to preserve. The Edelgrappa F150NE is a battery-powered cutter designed for heavy-duty rescue applications. It incorporates a brushless motor to provide stable torque output, reduced wear, and high durability under continuous load. With a weight of 8.6 kilograms, the unit offers optimized maneuverability while maintaining cutting stability. The tool is NFPA 1936-2020 compliant, ensuring conformity with international safety and performance standards. Operating on a cordless power system, it delivers full mobility without reliance on external power sources. Cutting performance covers cables and various structural materials, supported by a compact, robust housing. The F150NE ensures efficient force transmission, minimal vibration, and reliable performance in critical field operations. The giant tire shredding machine, model BS6000 by JECC, represents a complete industrial solution for high-capacity tire recycling. Designed for efficiency and durability, the machine handles large volumes of tires, converting them into manageable shredded material suitable for further processing or disposal. The BS6000 shredder is equipped with reinforced cutting blades capable of processing thick and large diameter tires, maintaining precision and consistent output size. Hydraulic and mechanical drive systems deliver high torque and controlled cutting speed, optimizing energy efficiency while reducing wear on critical components. Safety mechanisms, including emergency stops, overload protection, and operator shielding, are incorporated to comply with industrial safety standards. Material flow is managed via automated feed rollers and conveyors, ensuring uniform input and preventing jams. The modular design allows for easy maintenance, replacement of cutting blades, and adjustment of shred size according to application requirements. The system supports integration with sorting, magnetic separation, and dust collection units for downstream processing. The giant BS6000 tire shredding machine is widely applied in tire recycling facilities, waste management centers, and material recovery operations. Its engineering focuses on high throughput, operational reliability, and long-term durability, making it a benchmark in industrial tire shredding technology. The production of high-quality rubber mat rolls with colored flex for gym flooring involves a precise, multi-step process that ensures durability, aesthetic appeal, and functionality. Designed for wholesale distribution, these mats are manufactured using EPDM rubber crumbs and polyurethane PU binders, resulting in robust, vibrant flooring solutions. Below is a detailed overview of the manufacturing process, seamlessly integrating each step to produce consistent, high-performance rubber mats. Primary activities consist of breaking down EPDM seal strips into fine crumbs. This initial step transforms raw EPDM material into small, manageable granules suitable for further processing. The crumbs are then sifted to remove impurities, such as dust or debris, ensuring only clean, high-quality material proceeds to the next stage. This meticulous preparation is critical for achieving a uniform and durable final product, setting the foundation for the subsequent mixing process. Next, the cleaned EPDM crumbs, including colorful flecks for aesthetic appeal, are loaded into a mixer. For every 8 kilograms of crumbs, 1 kilogram of PU binder is added to ensure proper binding and structural integrity. The mixture is blended for 8 minutes to achieve uniform consistency, a crucial step to ensure the colored flecks are evenly distributed and the binder coats each crumb thoroughly. This uniform mixing enhances the mat's strength and visual appeal, preparing it for molding. The mixed crumbs are then transferred into a mold, a process that takes approximately 15 minutes to completely fill the mold. Once filled, the mold is subjected to a hydraulic press applying 31.5 megapascals of pressure. This high-pressure pressing compacts the crumb mixture, ensuring a dense and cohesive structure. The mold is then fixed in place and left for 24 hours to undergo vulcanization, a chemical process that strengthens the rubber by forming cross-links, enhancing its durability and resilience. After vulcanization, the solidified rubber column is carefully removed from the mold. The column is then mounted on a whirling machine equipped with a new diffusion knife for each column to ensure precise cutting. The machine's settings are adjusted to cut the rubber into sheets of varying thicknesses based on specific requirements. Computer-controlled cutting ensures accuracy, with each roll trimmed to the desired length. At the start and end of each roll, 1 meter is cut off to ensure clean, consistent edges, meeting customer specifications for gym flooring applications. Finally, the cut rubber sheets are rolled, printed with branding or specifications if required, and packaged for wholesale distribution. This final step ensures the mats are ready for delivery, maintaining their quality during transport. The entire process, from breaking down EPDM strips to packaging the finished rolls, is designed to produce durable, visually appealing rubber mats with colored flecks that meet the rigorous demands of gym environments. Through this streamlined and precise manufacturing process, high-quality rubber mat rolls are produced efficiently, offering both functionality and aesthetic appeal for gym flooring applications. Each step is carefully executed to ensure consistency, durability, and customer satisfaction, making these mats a reliable choice for wholesale buyers. Bruck GmbH provides complete welding and fabrication solutions within a single facility, streamlining production and eliminating transportation delays. Components are manufactured, machined, and assembled to exact specifications. The facility supports all common welding methods, including manual and automated electroarc, MIG/MAG, TIG, and submerged arc welding. Advanced processes enhance wear and corrosion resistance. Turntables accommodate heavy components, handling up to 30 tons with diameters from 50 millimeters to 4 meters. The workflow integrates forging, rolling, machining, and assembly, ensuring precise dimensional control and consistent quality throughout the production chain. The boring mill vertical turning machines used in industrial gear manufacturing are designed for precision machining of extremely large components. An open-side vertical turning mill with a 20-ton table can handle diameters from 0 to 20 feet, with adjustable columns allowing expansion up to 50 feet. This flexibility enables the machining of gears as large as 40 feet in diameter, proven reliable over decades. Equipped with a live spindle, the system allows drilling and tapping of bolt circles without repositioning the workpiece. A 2-meter vertical turning center from Giddings & Lewis further enhances capability, supporting diameters up to 94 inches. With dual live spindles and integrated pallet changing, it performs turning, drilling, tapping, and milling in a continuous process, maximizing productivity and reducing setup times. The 4-axis CNC milling machine with an automatic tool changer, ATC, represents a major step forward in precision manufacturing. Unlike conventional 3-axis systems, the 4th axis provides rotary motion, typically the A-axis, enabling machining on multiple faces of a workpiece in a single setup. This reduces repositioning, ensures higher accuracy, and allows the creation of complex geometries, such as helical surfaces, slots, and contoured profiles. The integration of an automatic tool changer further enhances productivity by eliminating manual intervention. Tools are stored in a magazine and exchanged automatically, minimizing downtime between operations such as drilling, milling, and contouring. This combination of automation and multi-axis control delivers tighter tolerances, superior surface finishes, and faster cycle times. These systems are widely applied in aerospace, medical device, mold making, and automotive industries, where precision and repeatability are critical. Capable of machining materials ranging from aluminum to hardened steel, the 4-axis CNC with ATC provides a balance of flexibility, efficiency, and scalability, making it indispensable in modern high-precision manufacturing. CNC mill-turn machining integrates both milling and turning operations within a single setup, enabling highly efficient manufacturing of complex components. Step Rapid operates advanced CNC machines with multi-axis capabilities, including 3-axis, 4-axis, and 5-axis configurations, providing flexibility to shape features such as internal forms, pockets, and complex external geometries. This approach significantly reduces setup time by eliminating the need for secondary operations and multiple fixtures. Live tooling and automation enable simultaneous milling, drilling, tapping, and turning, ensuring tight tolerances around plus or minus 0.005 inches, 0.127 millimeter, and excellent surface finish, all within continuous machining cycles. Materials such as aluminum, stainless steel, titanium, and engineering plastics are routinely processed. Standard components including prototypes, housings, and toolings benefit from rapid turnaround, often in under 5 days, thanks to integrated tool changes and streamlined workflows. This mill-turned approach enhances productivity, maintains high repeatability, and supports flexible production volumes, making it ideal for both prototype development and low-volume manufacturing runs in industries demanding accuracy and complex geometries. The Great Wall Steel Casting Company has established itself as a leading enterprise in the heavy steel casting sector, specializing in the design and production of large-scale components such as slag pots and slag ladles. The foundry is equipped with advanced smelting facilities, precise machining equipment, and digital engineering systems, which together enable the delivery of high-quality customized castings for the metallurgical industry. The production process begins with digital modeling and CAE simulation. By applying computer-aided engineering tools, the foundry is able to predict potential defects, such as shrinkage cavities, porosity, or thermal stress in advance, This step allows engineers to optimize gating and riser systems, ensuring a controlled solidification path and minimizing rejection rates. Once the design is validated, high-quality steel materials are charged into the electric arc furnace for melting. Strict raw material selection and spectrometer testing guarantee precise alloy composition to meet mechanical property requirements. The molten steel is then refined and treated to remove impurities, ensuring superior toughness and resistance to thermal cycling. For slag pots, which serve as load-bearing vessels for molten or solid slag and steelmaking, durability and dimensional stability are paramount. The casting molds are prepared using advanced molding lines, ensuring uniform compaction and dimensional accuracy. After the molten steel is poured, controlled cooling methods are applied to reduce internal stress and enhance structural integrity. The unique design of the slag pot includes a bowl-shaped body with integrated lifting lugs for crane handling. Inside the pot, a grill structure is placed below the surface, under at least 300 millimeters of the upper surface, and divides the inner pot into some pieces. Dividing the interior into compartments to withstand thermal shock and distribute slag weight evenly. This innovation improves performance compared to conventional designs. After solidification, the casting undergoes rigorous heat treatment to optimize hardness, strength, and resistance to deformation under extreme temperatures. Dimensional machining and surface finishing are performed on heavy-duty CNC equipment, ensuring that all specifications are met with tight tolerances. Quality control is maintained through non-destructive testing, NDT, ultrasonic inspection, and load-bearing simulation analysis. Each slag pot or ladle is validated for structural integrity before delivery. Compared to traditional casting processes, Great Wall's method significantly reduces cycle time, enhances service life, and decreases scrap rates. Through continuous process innovation, Xinxiang Great Wall Steel Casting Company Limited provides metallurgical enterprises with slag pots and slag ladles featuring shorter production cycles, longer operational life, and higher resistance to mechanical and thermal deformation. These advantages make the company's products highly reliable in demanding environments such as steel plants, foundries, and non-ferrous metallurgy operations. Valkovny Trub Chomutov is a historic producer of seamless steel pipes, continuing a tradition established by the Mannesmann brothers in 1890 with modern hot rolling technologies. The facility manufactures seamless pipes with outer diameters ranging from 273 millimeters to 660 millimeters and wall thicknesses between 9.5 millimeters and 72 millimeters, using various grades from carbon to high-performance alloys like P92. The rolling process employs the Mannesmann piercing method in pilger mills for hollowing and reducing cross-sections. High precision is achieved through standardized processing, supported by ISO certification and international norms. The manufacturing of cast steel valves requires a combination of advanced casting methods, precision machining, and rigorous quality controls to produce components capable of withstanding extreme pressures and corrosive environments. Two primary casting methods are applied: investment casting, also known as the lost wax process for smaller valve components, and sand casting for larger diameter bodies. In investment casting, the process begins with wax injection into permanent dies to create precise patterns. Each wax pattern is marked with a unique heat number for complete traceability. Skilled operators assemble wax runners, risers, and flow channels onto the wax patterns, enabling the controlled delivery of molten metal during pouring. These wax assemblies are then dipped into refractory slurries and coated with fine sands in successive layers to build a ceramic shell. Typically, 7 to 9 coats are applied, with each coat cured before the next is added, forming a strong, heat-resistant mold. Once cured, the wax is removed by immersing the shells in hot water or steam, leaving behind a hollow cavity that replicates the intended component geometry. The ceramic shells are fired in furnaces at up to 800 degrees Celsius, which strengthens the mold, eliminates residual wax, and ensures the mold is preheated to promote proper metal flow. In parallel, molten steel is prepared in induction furnaces. The chemical composition of the melt is controlled by spectrometer analysis. Once verified, molten steel is poured into the preheated shells under carefully regulated conditions to minimize shrinkage and voids. For larger valve bodies, sand casting is used due to the high volume of molten metal required. A wooden or metal pattern is placed into a mold box and tightly packed with special sand mixtures. Chemical binders or carbon dioxide curing agents are used to harden the sand, and once the pattern is removed, a cavity in the shape of the component remains. Cores are inserted to form hollow sections, and the two mold halves are clamped together, coated to resist erosion, and filled with molten steel. After solidification, the sand mold is broken apart, and the casting is released for cleaning. Following either casting method, the solidified parts undergo knockout, where shells or sand residues are removed and the gates and risers are cut away. The castings are then grit blasted to eliminate remaining oxides or deposits. Heat treatment cycles, such as normalizing, quenching, and tempering, are applied to refine the grain structure and ensure mechanical strength, ductility, and toughness. Once heat-treated, the castings proceed to finishing, where grinding removes sharp edges and surface irregularities. Dimensional inspections are conducted with calibrated instruments, and many components are subjected to radiographic testing to detect internal discontinuities. Rust prevention coatings are applied to stabilize the surfaces before machining. Once testing is complete, the valves are prepared for painting. Protective primers and final coats are applied on the external surfaces, with sensitive areas such as stem threads, sealing faces, and nuts carefully masked to avoid contamination. After painting, the valves are serialized, documented, and moved to the finished goods warehouse. The completed products are now ready for shipment to customers across power generation, petrochemical, and water distribution sectors. Over a decade ago, the forging operations at JK Forging followed a traditional yet reliable workflow built on core metallurgical practices. The process began with heating steel billets in oil or gas-fired furnaces until reaching forging temperatures of approximately 150 to 250 degrees Celsius. At this stage, the material achieved sufficient plasticity for shaping while maintaining structural integrity. Once removed from the furnace, billets were transferred immediately to mechanical hammers or hydraulic presses, where controlled impact energy was applied to elongate, compress, and refine the grain structure. Following this initial deformation, the red-hot blanks were placed into pre-machined steel dies for closed die forging, where high compressive forces drove the metal to fill cavity details, producing near-net shape components such as gears, shafts, or flanges. Excess flash was trimmed off in secondary pressing steps. Unlike today's rapid quenching methods, parts were often subjected to natural cooling in ambient air, a technique that minimized internal stresses but delivered slower production cycles and less consistent microstructural control. At that time, the production cycle relied heavily on manual labor, with workers responsible for handling billets, operating furnaces, and positioning components under the hammer or press. Machinery was relatively basic and semi-mechanical, requiring frequent human intervention and skillful coordination. Personal protective equipment was minimal compared to modern standards, with many workers exposed to heat, noise, and heavy physical effort. This combination of high manpower requirements, limited mechanization, and low safety measures characterized the forging industry's operational environment more than 11 years ago, reflecting both the resilience and challenges of traditional forging technology. Helical. Industrial Machinery Corporation, IMC, headquartered in Ludhiana, India, is a leading manufacturer of high-precision bolt-making machines engineered for industrial-scale production. The company's product line includes automatic bolt head trimming and shank-reducing machines, bolt threading machines, cold heading machines, and thread rolling machines. Each system is designed for robustness, precision, and high-volume output, integrating advanced automation to ensure consistent performance, reduced downtime, and minimal manual intervention. Bolt threading machines deliver accurate, uniform threads on bolts, rods, and pipes, adhering to strict dimensional tolerances required in automotive, construction, and heavy machinery applications. Cold heading machines form bolt heads through high-speed deformation processes, producing uniform shapes without compromising material integrity. Thread rolling machines utilize cold forming techniques to enhance thread strength and surface finish, while the bolt head trimming and shank reducing units ensure final dimensional accuracy and surface quality. IMC machines incorporate user-friendly control panels, automated feed and alignment systems, and high-capacity drive mechanisms, supporting continuous operation in demanding production environments. Maintenance and part replacement are facilitated through modular designs, accessible components, and durable materials. Advanced mechanical engineering and precise calibration minimize residual stresses during cold working processes, preserving structural integrity of the fasteners. The machines accommodate a wide range of bolt diameters and lengths, providing flexibility for diverse industrial applications. Material handling is streamlined, with automated conveyors, feeding devices, and synchronized operations between modules to optimize throughput. Safety features, including emergency stop systems and protective housings, ensure secure operation during high-speed manufacturing processes. IMC's engineering approach combines precision mechanics, material science, and process automation, delivering reliable, high-performance bolt-making machines. These systems are capable of supporting large-scale industrial operations while maintaining global standards for quality, efficiency, and durability, making IMC a preferred partner for manufacturers requiring engineered fastening solutions worldwide. Wind. The V2 3-axis cone forming machine is a specialized sheet metal forming system designed to produce conical shapes with high precision and repeatability. Built on a robust frame, the machine integrates 3 independently driven forming rollers positioned in a triangular configuration. Each axis is servo-controlled, allowing synchronized movements that gradually bend flat metal sheets into cones without the need for pre-welding or complex manual adjustments. The forming process begins by positioning the metal sheet between the rollers. Through programmed pressure and rotation, the rollers apply progressive forming forces that shape the material into the desired conical geometry. The 3-axis configuration provides greater flexibility compared to traditional 2-roller systems, enabling the production of cones with varying taper angles, diameters, and wall thicknesses. The machine supports a wide range of metals, including stainless steel, carbon steel, and aluminum. Its CNC control system allows precise parameter input, ensuring consistency across production batches. Safety systems, hydraulic supports, and automated alignment features further enhance efficiency and reduce operator workload. Widely used in industries such as ventilation, metal fabrication, construction, and energy, the V2 cone forming machine delivers accuracy, durability, and productivity in cone manufacturing applications. A tandem press brake for street pole fabrication employs synchronized dual machines to enable ultra-long, precise bending, ideal for tapered light poles and utility columns. It utilizes the Delum DA52 CNC control system, managing Y1 and Y2 axes through hydraulic proportional valves with linear scale feedback, ensuring parallelism within plus or minus 0.01 millimeters. An automatic front feeding system driven by variable frequency motors positions steel blanks accurately before bending, while electronic crowning compensation maintains consistent bend angles. This configuration delivers repeatable, high-precision bending of extended and tapered workpieces, enhancing productivity and accuracy in street pole production. The Vatac twin isolation lubricated plug valve features double independent plug closures, providing reliable sealing and control. Designed for rough machining and heavy-duty applications, it is ideal for double block and bleed systems, ensuring safety, precision, and durability in industrial fluid handling operations. Maze,